Okay, so welcome. So we're basically done with chapter three now. If you didn't get a chance to watch the makeup lecture over the weekend, that's fine. I will flash a couple of these things on the screen. So main things that we talked about were properties of the determinant, especially as related to elementary row operations. So the main points were elementary row operations. So row replacement doesn't alter the determinant. Row swapping flips the sign of the determinant, and row scaling scales the determinant. Okay, those are the most important bits of yesterday's. Well, that's not the most important bit, but this is the stuff that allowed us to say what was really the most important thing, which was this fact that a square matrix A is invertible if and only if its determinant is not zero. So literally the determinant determines whether or not a matrix has an inverse. So this is the most important fact about the determinant. It's the entire reason we developed the determinant to begin with, is to have a way to answer that question of, is the matrix I'm dealing with invertible or not? So that's a really important question to ask, because if you're dealing with an invertible matrix, basically everything you want to do is nice. And so it's nice to know whether or not you're in that situation. And so the determinant 100% answers that. It completely characterizes invertible matrices. Okay, and then some last facts that tidied up. So the determinant of a transpose of matrix is the same as the determinant of the matrix. Uh, Determinant of a product of matrices is actually the product of the determinants. So while matrix multiplication maybe doesn't behave as well as you'd like, with respect to the determinant, it does. Okay, in this way. All right. So those are the important things. Anyway, so if you haven't watched that yet, I encourage you to watch that at some point, because it introduces a couple of nice tricks for computing determinants. So anyway, um, so tidying up then, there's a few. There's a there's a couple of neat things to mention about determinants. So you might actually remember having seen this somewhere before. So the first is Cramer's rule. It's not something we're going to be using very much in the course, but it is a funny thing. So let A be an n by n matrix, and let B be any vector in Rn. It doesn't matter. Okay, and let A sub I of B be the matrix obtained from A by replacing its ith column with the vector B. Okay, so that's weird. I'm going to write out what that looks like. All right, so if it has the normal column vectors like A sub 1, A sub 2, and so on, and then out to the ith position, instead of having A sub I here, it has B. So this is the ith column. And then after that, it's normal. So I have A sub I plus 1, and so on, all the way up to A sub n. So this is the matrix I get by replacing the ith column of A with the vector B. Okay. All right. So what am I doing? Why am I defining this thing? So I have the following theorem, which is called Cramer's rule, which gives us a funny way of solving linear systems using this quantity. Okay, so let A be an n by n matrix that is invertible. Okay, so let it be invertible. Then for any B in Rn, the unique solution to AX equals B has entries given by, so the x sub I slot can be computed as the determinant of this a sub I of b thing over the determinant of a. So now you see why a needs to be invertible. For this thing to have a prayer of working, since you're going to be dividing by the determinant of a, that can't be 0, and so that means that a has to be invertible, right? And this is for I going from 1 to n. Okay, so this might seem a little confusing at first. I'm not going to write out the proof of this, but it's actually a fairly short proof of why this works. So you can see that. So the proof of this is on page 180. So it's at the top of page 180 in the textbook. Although, well, that's in my edition. I guess in your edition it might not be that, but it's in 3.3, and it's a short proof. So let's do a quick example that shows how to use this, and then we'll move on, since, as I said, we're not gonna do this very much in this course, but it's a neat thing anyway. So I want to use Cramer's rule to solve the following system, which is 3x sub 1 minus 2x sub 2 is equal to, no, not 0. Let's make it 6. Okay, so 3x sub 1 minus 2x sub 2 is equal to 6, and minus 5x sub 1 plus 4x sub 2 is equal to 8. Okay, so then looking at this system, what is our A? So our A is the matrix 3 minus 2 minus 5, 4, and our B is the vector 6, 8. Right. Okay. What's the determinant of A? So the determinant of A is 3 times 4, so that's 12, minus 10, so that's 2. So determinant of A is 2. And so let's write out what is A sub 1 of B. So A sub 1 of B is the matrix where I have replaced the first column of A with B. So that's reading column-wise now, 6, 8, minus 2, 4. Okay, and then A sub 2 of B is A, except I've replaced the second column with B. So reading column-wise, again, this is 3, minus 5, and 6, 8. Okay. All right, and so if I wanted to know what x sub 1 and x sub 2 solve this system, using Cramer's rule, x sub 1 is the determinant of A sub 1 of B over the determinant of A. But this is, so the determinant of A sub 1 is 24 minus 16, so that's 24 plus 16 over 2. So 24 plus 16 is 40, divided by 2 is 20. And x sub 2 is the determinant of A sub 2 of B over the determinant of A. So A sub 2, the determinant of A sub 2 of B is 24 plus 30 divided by 2. So 54 divided by 2, so that's 27. Yeah. So that's it. So it might be a little bit mysterious, why this works, but if you want to see why this works, you can look at the proof of Cramer's rule to see why it works out in this way, why this is a neat sort of shortcut where you can, it's not always a shortcut, but sometimes it's a shortcut where you can actually compute this strictly in terms of the determinant, right? This is a ratio of some determinants once you set it up like this. So Anyway, Cramer's rule is kind of a neat thing, and I think I assigned one Cramer's rule problem as part of your homework set. When would this be practically useful? So, I believe that I believe best the place where this might be most practically useful is um, basically when you apply this to there's an application I believe to Laplace transforms arising from study of ODEs that come up in various applications of engineering. So if you have some of the parameters, the Laplace parameters that actually show up in your linear system, then using Cramer's rule, you can actually isolate these as the Laplace transform of some quantity. So I believe there's an example of this actually done in my version of the textbook. I think there's an example of this done, but we're not going to get into that stuff. But I think like that's one off the top of my head. I think that's one application of this. Now whether it's actually the most efficient thing to do in a given situation, I'm not sure that Cramer's rule is ever the most efficient thing to do. But anyway, this is a neat thing. And what's nice, of course, is that you can isolate individual entries as ratios of the determinants here. So anyway, another fact that is neat is the following. It turns out that there is a general formula for A inverse. This is something called the classical adjoint. This is called the adjugate or classical adjoint formula. So what is this? Basically, here it is. Let A be an invertible matrix, and we'll say it's an n by n matrix. Then A inverse is equal to 1 over the determinant of A times the adjugate matrix of A. What is the adjugate matrix of A? So the adjugate matrix of A is the matrix of transposed cofactors. And what do I mean by that? This is 1 over the determinant of A times the matrix of cofactors. So the first entry is C11. So across the diagonal, it's actually symmetric. But then this entry is the C12 entry, and this is C13. And all the way down to C1n. So notice that the subscripts are not running in the way that they normally do. They're running in the transposed way. Right? So typically, the subscripts that you use to describe a matrix, this would be the second row, first column entry, but the subscripts are flipped here. So similarly, this would be the C21 entry all the way out to the CN1 entry here. On the diagonal, things are kept the same. And so that's what I meant by transposed cofactors, where the C sub ij are cofactors, are the ij cofactors. Now, this is my expression for this. Of course, in a simpler way, I write it like this. So I write without all of the the explainers here. A inverse is 1 over the determinant of A times the adjugate of A. So is this very useful? Well, typically this is a lot of work to compute. Typically, right, for this course, it's not going to be very useful for us to actually use this adjugate formula for the inverse of a matrix. It would actually be better for us to just do the standard algorithm. So this is mostly for theoretical computations, and the same is true for Cramer's rule. So both Cramer's rule and the adjugate formula are mostly for theoretical computations. Okay, so if you're actually tasked with doing some of this stuff by hand, you wouldn't really use these. Methods. So anyway, note that these are the transposed, right? These are transposed. Now, because this is not going to be something that you're going to be doing a lot by hand, I wanted to show one neat thing about this. Okay, so I wanted to show one neat thing about this, and it's the following. So I want to do a single example. What if A is the matrix A, B, C, D? So it's a 2 by 2 matrix. Okay, and assume A is invertible. Okay, so I want to use the adjugate formula to compute A inverse. So I want to use the adjugate formula to compute A inverse, i.e., A inverse is equal to, by the adjugate formula, let's run it back for a second. A inverse is 1 over the determinant of A times the adjugate of A. So this is 1 over the determinant of A times the adjugate of A. Okay, so here, this is equal to, of course, the determinant of A is AD minus BC. Since A is invertible, I know that that's not 0, so dividing by it's no problem. So this is 1 over AD minus BC times, what is the adjugate of A here? The adjugate of A is the one, so I know the diagonals are unchanged. So that's C11 and C22, but then this is C12 and C21. But let's compute what these cofactors are. So what is C11? C11 is minus 1 to the 1 plus 1 times the determinant of the matrix A11. What is the matrix A11 for a 2 by 2 matrix? It is the matrix that I get when I ignore the first row, first column. What matrix is that? It is the 1 by 1 matrix D. What's the determinant of a 1 by 1 matrix? It's just the number itself. It's just D itself. So what is this? Minus 1 to the 1 plus 1. That is 1 times the determinant of the 1 by 1 matrix D. That's just D. Okay. C21 is going to be minus 1 to the 2 plus 1 times the determinant of A sub 2, 1. What's A sub 2, 1? A sub 2, 1 is the 1 by 1 matrix I get when I delete the second row, first column. That's B. Minus 1 to the 3 is minus, so this is minus B. C12 is minus 1 to the 1 plus 2 times the determinant of A12. Okay, what is A12? It's the matrix I get from A by ignoring the first row, second column. So it's C. This is minus 1 cubed, so this is minus C. And then C22 is minus 1 to the 2 plus 2 times the determinant of A22. A22 is the matrix I get from ignoring the second row, second column. So it's A. And this is minus 1 to the 4th, so it's just 1. So this is A. So let's put this in here. So this is 1 over AD minus BC times the matrix. C11 is D. C21 is minus B. C12 is minus C. And C22 is A. Oh. That's our usual inverse formula, right? Okay. So this is showing how this adjugate formula would work for a 2 by 2, right? So you can actually use this to come up with, I say, analogous formula for a 3 by 3. The real problem with this is it's just this adjugate thing is just not as nice for 3 by 3s, and it's not basically beyond writing it like this. You don't really have much of a formula because this adjugate is just not a convenient quantity to deal with. But anyway, I wanted you to see that anyway because it's an interesting thing. Okay. So that's that. So you can use this adjugate formula to compute the inverse of something. So next, the thing I wanted to talk about shows the geometric intuition behind what is going on with the determinant. So this explains, and maybe it doesn't really explain because this is actually, again, just a result of alternating sums of things being interesting for various reasons. So determinants as areas or volumes. And really what I should say here is the relationship between determinants and areas or volumes. Okay, so you may have already seen the following fact before, but if A is a 2 by 2 matrix, so if A is a 2 by 2 matrix, then the area defined, or I should say the area of the parallelogram determined by the columns of A is the absolute value of the determinant of A. Okay. And if A is a 3 by 3 matrix, then the volume of the three-dimensional analog of a parallelogram is a parallelepiped. So the volume of the parallelepiped determined by the columns of A is absolute value of the determinant of A. And why stop there? If A is a 4 by 4 matrix, then the hypervolume of the hyperparallelepiped determined by the columns of A is the absolute value of the determinant of A. Right? And I can keep going. It doesn't have to stop there. The dimension doesn't matter here. The same thing is going to hold true. Okay. So, what is the picture here? So first of all, you might have some questions. What do I mean by the parallelogram determined by the columns of A? So let's say that I have a matrix A, and let's say that it's a 2 by 2 matrix. So it's a 2 by 2 matrix, and it has two columns. So A1 and A2. What do I mean by the parallelogram determined by the columns of A? Well, I have my plane here. Here's the origin or the zero vector. We're going to talk about vector geometry stuff a little bit later. I know we've mentioned some very basic stuff already, but we're going to talk about more of this stuff actually in chapter 6 later. But let's say, so I have two vectors, a1 and a2. So just for the sake of this picture, say that a1 is this ordered pair, so then I get an associated vector, of course. And it looks like that. So that's a1. And we'll say that here is my vector a2. Okay. Then, since these are in general position, okay, I actually get a parallelogram out of this. So what is the associated parallelogram? These determine the obvious parallelogram where this other vertex is, the sum of these vectors. What is the only time that I don't get this parallelogram? Okay, what if I have two of these vectors and they're not in general position like this, right? They line up, they're parallel. What then? What is the parallelogram determined by those two vectors? Well, parallelogram determined by those two vectors is nothing. It's a line. It's not even a parallelogram. What's the area of a line? 0. Oh, I wonder what that means about the determinant of the matrix. Right? So if I had a matrix A that had columns that were parallel, right? So 2 by 2 matrix A, and two of its columns were scalar multiples of each other, what happens? Well, its determinant's 0. So this even takes care of that degenerate case when these columns line up and they're not in general position, so that I don't actually get a proper parallelogram. Okay, so the area then of this parallelogram is the determinant. So area is the absolute value of the determinant of the matrix A, whose columns are that. Now, in 3 dimensions, the same thing is true, but I'm not going to bother drawing a picture. But this is what's going on here. Okay. All right. So that's the first nice thing about, or the first nice tie-in between determinants and areas or volumes. But a really, really nice fact that you have already seen in Calc 3 in another form. This is actually a simpler form than you've seen in Calc 3 because the types of transformations are much more restricted. But it turns out that a lot of those Calc 3 examples you did of this they actually used linear transformations anyway. And so a lot of times in Calc 3 when you were doing change of variables, you were actually using this following theorem. So how about linear transformations and the determinant? So there's the following theorem. Okay, so let T maps R2 to R2 be a linear transformation with standard matrix A if S is a parallelogram in R2, then the area of the image T of S, okay, so the area of the image of this parallelogram under this map T is equal to the absolute value of the determinant of the standard matrix A times the area of S. Another way of saying this is that the absolute value of the determinant of A is the scale factor, right, in measuring the area of the transformed region. So the area of the transformed region is the absolute value of the determinant of A times the area of my parallelogram. A couple things to note here, okay? One, what if the determinant of A is plus or minus 1? If the determinant of A is plus or minus 1, this statement says that a transformation T having a standard matrix that has determinant plus or minus 1 doesn't affect the area of this parallelogram. So you can map that parallelogram with T. It does something to it. Okay, but whatever it does to it, it doesn't actually change its area. Okay, so that's if the standard matrix for T has determinant plus or minus 1. Now, what if the determinant of A is 0? So what if the linear transformation in question is one that has a standard matrix that is not invertible? Okay, what happens there? Well, in that case, this standard matrix does something that squishes or, collapses some of the dimensional data that you have and makes this 0. The area of the transformed region is 0 times this area, so it's just 0. Okay, so think about what transformations would do that, right? What if I had a transformation that was projection, right? So it took a point in R2 and projected it onto one of the axes. So it projected it onto the x-axis, it projected it onto the y-axis, or it projected it onto some line, right? Okay, so what is happening there? You're squishing geometric data, right? You're squishing that area data. So instead of having a rectangle, for instance, that would get squished to be a line segment on one of the axes. And the area of a line segment, of course, is 0, right? So is the determinant 0 if the columns are linearly dependent? Yes, that's true. Okay. Conversely, if the determinant is not 0, it means the columns are linearly independent. Okay, so this is an important fact. This is going to get, in our invertible matrix theorem, eventually we're going to have some things that we add to it, basically. But yes, being invertible is a very, very nice thing and says exactly that thing. So a matrix being invertible means that its columns are linearly independent. That's right. Okay. And yeah, someone also mentioned the Jacobian. So the Jacobian was a determinant, right? So when you have the Jacobian showing up underneath that integral in change of variables in Calc 3, the Jacobian is a determinant. And what happens if you use a transformation in your change of variables that's Jacobian is 0? Well, in that computation of your triple integral, right, or your double integral, underneath the integral sign, you would have a 0 showing up. So your whatever integral you're computing would be 0. It'd be nonsense. And the reason why is because using a transformation that has 0 Jacobian would be bad. You'd be squishing the data in such a way that it's unrecoverable. Okay, and so that's what's going on here. All right, similarly, if T is determined by a 3 by 3 matrix A, and if S is a parallelepiped in R3, then volume of TS is equal to the absolute value of the determinant of A times the volume of S. Okay, so I'm not going to give the proof for why this is, but this is a nice fact. Now it turns out that so here we began with regions S. So S was a parallelogram in the two-dimensional case. In three-dimensional case, S was a parallelepiped. Actually, it doesn't matter what S is. So S can be any region with finite volume, with finite area volume, It doesn't matter if S is a parallelogram or a parallelepiped. Um, it's just easier to prove in those cases. But it turns out S can actually be any. It doesn't have to be a parallelogram or parallelepiped. It can be any region. So S could be, in this case, S could be, right, like an ellipse in its interior, right? So there's lots of possibilities for pictures here. Okay. So anyway, this is a final nod of telling you basically what is important about the determinant, or rather giving you maybe more motivation for why the determinant's important, because it's intimately tied in with the geometry going on in R2 and R3. Okay. So we are done with chapter 3. Right, so we move on to chapter 4, which is abstract vector spaces. Okay. So what is the idea here? Okay. Replace Rn with an abstract vector space. V. Okay. And study general properties of whatever this V is. Now, why would I do this, right? So why would I ever replace my Rn that I know and love and enjoy because it's simple to do the calculations I'm familiar with? Why would I replace that with an abstract vector space V where I, don't necessarily directly have the same thing going on that I have in Rn? So one, I'm going to have the same stuff going on in V that went on in Rn. Okay. So then you might say, well, then where is the benefit in replacing these, right? First of all, maybe the most basic question is there ever like a setting, right, where I can say something about V that I wouldn't be able to do if I had just stuck with my description of Rn instead? And the answer to that is, if V is what's called finite dimensional, so we'll talk about that a little later in this chapter, but if V is finite dimensional, then a vector space that has dimension n is the same thing as Rn. Okay, so I have to say a real vector space in that case. So a real vector space that has real dimension n is actually the same thing as Rn. So then you might say, then what am I doing? Why am I going through all of this hassle to introduce all these abstract notions when I could just deal with Rn? So there's something that we can say. We're not going to spend much time on it in this course, but there are properties of Rn that carry over that are actually a result of more abstract properties called vector space axioms that don't just apply to Rn, but they apply to spaces that they don't seem like they are similar to Rn, but they are. And in order to see that, or to make it easier to see that, we talk about abstract vector spaces instead. So the easiest example of this is if you've had 246, if you've had differential equations, or if you study anything about differential equations, not necessarily in Math 246, but anywhere else you've seen it, the study of ordinary differential equations uses, to a huge degree, it uses a lot of the machinery of vector spaces and linear algebra, even though the spaces that you're dealing with in question are actually spaces of functions. Okay, but there's a lot of nice stuff that comes out of the machinery of differential equations that is using linear algebra stuff, even though the vectors are functions. Okay, for example, Okay, and so there's a lot of reasons why you would want to study like the basic properties of V here. Okay, so what is a vector space? So rather than write all of these, I'm going to put this list on camera. We're going to go through the list because you're never in this course going to be asked to verify this list of axioms here. Okay, here, let me hold it up. Okay, so what is a vector space V? A vector space is a non-empty set V of objects, which we are going to call vectors, okay, so on which are defined two operations, vector addition and multiplication by scalars. Our scalars are going to be real numbers, okay? I'll talk about that in a second. So subject to the 10 axioms or rules listed below. So axioms means these are things that are assumed true in this vector space. These are not proved. These are automatic facts you get. This is part of the definition of a vector space. So here's our list of axioms here. So these axioms must hold for all vectors u, v, and w and v, and for all scalars, that is real numbers c and d. Okay, so the first fact is a fact about closure. This is called closure. So this is the statement that if you have two vectors in V, their vector sum, u plus v, is also in V. That is just the statement that vector addition is closed. So you have two vectors in V, their sum doesn't lie outside of V, it still lies in V. Okay, vector sum is commutative. So u plus v is equal to v plus u. Okay, that's good. The third thing, vector sum is associative in this way. So if you have three vectors you're wanting to add, you can add them pairwise in any order. So note, I didn't change the order of u, v, and w. So reading from left to right, it's u, v, w, u, v, w. I'm just changing the association, right? I'm just moving the parentheses. Okay, although of course from number 2 I could change the order as well. Okay, so number 4, there is a zero vector, 0, in V, such that u plus 0 is equal to u. Okay, so there exists a zero vector that is the additive identity for vector addition. That's what number 4 says. Okay, for number 5, for each u in V, there is a vector minus u in V, such that u plus minus u is equal to 0. Okay, so this is the existence of an additive inverse. So this minus u is the vector sum additive inverse for u. Okay, number 6 says the scalar multiple of u by c, denoted by cu, is in V. Okay, so that's closure for scalar multiplication. Number 7 says that scalar multiplication is distributive in the vector slot, meaning that if I have a sum in the vector slot, I can distribute that scalar multiplication to each of those vectors. And it's also distributive in the scalar slot. So if I have a sum of scalars times u, I can actually distribute in that usual way that I'm used to in Rn. So number 9 says that I can change the order that I do the scalar multiplication in, so I can actually just multiply the scalars first before scalar multiplying. And then 10 says that 1 times u is u. Okay, so scalar multiplying 1 times the vector u is u. Okay, now I can easily verify that Rn satisfies all of those properties. And so Rn is an example of a vector space. So note, Rn satisfies all those properties, thus is a vector space. So it's an example of a vector space. Okay, but there are other examples of vector spaces. So let's look at another example. So how about consider I'm going to call the set C. Consider the set C, which is the set of all polynomials up to degree 2. The set of all polynomials up to degree 2. What do polynomials look like that are up to degree 2? So this is really the set of all things that look like a sub 2 x squared plus a sub 1 x plus a naught, such that a naught, a1, and a2 are, say, real numbers. Right? So if by polynomials we mean polynomials with real coefficients, we'll specify that. That's fine. Okay, then I have a set here. It's the set of all polynomials up to degree 2, so they look like that in general, right? So yeah, maybe a sub 2 is 0, so that you only have a linear thing, or maybe a sub 2 and a sub 1 are both 0, so you only have constants. Those are still examples of polynomials. So let's just quickly go through our list. So the set of all polynomials up to degree 2. Let's quickly go through our list here. So our list says, let's see, can I actually, yeah, here we go. All right, so here's my polynomials up to degree 2. Let's check that they satisfy all these things. So I would need, I need two operations, plus and scalar multiplication. Okay, wait, yeah, before I start, I need plus and scalar multiplication. So what's plus here? So what would a vector look like here, right? So I have vector sum u plus v, but how do I describe a vector of polynomials up to degree 2? Well, I mean, if I have a vector u and I use the usual notation, say u0, u1, u2, and v is v0, v1, v2. Does this actually describe this? Does this describe this vector? Or does this describe a polynomial of up to degree 2 here? Well, yeah, because this is just the vector of coefficients, right? But everything else is determined in the polynomial. So all the other things showing up in the polynomial are completely determined. So if I gave you a list, all right, just to show you, right? Let's continue this example. So like if I gave you, for example, in my C, I gave you the vector, I'm going to call it t. So I gave you the vector t, and my vector t is -3, 0, 2. Well, what is this, right? In my C that I've defined here, what is this vector? This corresponds to what polynomial? It corresponds to the polynomial 2x squared plus 0x minus 3. Right? So simplifying, it corresponds to the polynomial 2x squared minus 3. Right? So the vector -3, 0, 2 corresponds to this polynomial. Okay. So then how should I define vector sum here? Well, I define it the usual way. I define it as it's v0 plus u0, v1 plus u, or sorry, well, I've defined it in the opposite direction. Here, let me put actually, I'll write it on this page so that I have more room. So then if I have two vectors, u and v, and I sum them, what do I get? I would get u0 plus v0, u1 plus v1, and u2 plus v2, right? Does that actually make sense for polynomials? You can check that it does. Right? Similarly, scalar multiplication works exactly in the same way. It would be c u0, c u1, c u2. So in terms of polynomials, what does this mean? It's just addition of polynomials, just pointwise addition of polynomials, right? Pointwise addition of polynomials. And this is just multiplication of polynomial by a scalar, or by a real number, c. Okay, and then we can check. So going back to our list, we can just check. With those two operations, does it satisfy all these things? So if I take a polynomial or if I take two polynomials that I've written as vectors and I sum their result, is it still a polynomial of up to degree 2? Yeah, right? It's still a polynomial of up to degree 2. I can sum them in any order. It's associative. There's a zero vector. What's the zero vector in my set of polynomials with respect to this addition? It's just the zero polynomial. It's just 0, 0, 0, the constant function 0, right? Is there a minus u? Yeah, I just take the negation of every coefficient, right? So it's the polynomial with the negation of every coefficient. Scalar multiplication works in the same way, and all these things are true. So this C that I've written out is a vector space. Okay, it is a vector space. In fact, some of you might have identified that it is a vector space that is identical to another one that we already know. So you can say that in the chat if you figured it out. But it turns out that this vector space of polynomials up to degree 2 is already a vector space that is very familiar to you all. Okay, so anyway, one more thing I wanted to say and then I'm done. So note also that from these properties we can deduce that 0 times any vector u is the 0 vector. If I scalar multiply the 0 vector by any scalar, I still get the 0 vector. And the symbol minus u, this additive inverse, can be, of course, computed via scalar multiplication of u by minus 1. So these three facts are actually results from the definition of vector sum. And yes, and someone said R3. Is it the same as R3? Yes, it is. So how does an abstract vector space differ in general from any given R? Well, it turns out that an abstract vector space can be infinite dimensional. So I went back here. I can go back here. I limited myself here. I said let C be the set of all polynomials up to degree 3. What if, up to degree 2. What if I just said let C be the set of all polynomials? So degree doesn't matter. Degree is arbitrary. It could be, you could have degree 500 polynomials here. You could have degree 500 billion polynomials here. There's no upper limit on the degree. How many entries would I need in these vectors to describe the set of all polynomials? Well, infinitely many, right? Arbitrarily many slots I would need here. And yet, even so, that would still be a vector space. Okay? And so, using all of the properties that we're going to discuss in chapter 4, we could say some things about that vector space, whereas that is going to behave differently from how Rn behaves. Now, in this course, we're not going to say too much about it, so we're not going to get too much from that particular angle. But this is you're being buttered up for later things, later types of analysis you might want to do on more complicated spaces. But yes, as someone said, R3 is the set of all polynomials up to degree 2. We'll talk about later how that's actually the same as R3. Okay. So that's the nice thing. So anyway, so that's it. And yeah, someone also said you can, so instead of using any of those things that you've proved about vectors in R3, you could do using polynomials here. We'll do some specific examples of where this is interesting later, especially when we talk about change of basis and stuff. So anyway, but that'll come later. So that's all for today. Someone's saying, when is going to be the test? The test's going to be next week, so I'll put out an announcement later today explaining all about the exam. So it'll be next week. No sooner than next Wednesday. Okay. So anyway, so I will see you all later. I'll see you all on Wednesday. So we'll keep going in chapter 4 that we just started.